Hello, in this video, we will be looking at how to find a node in a binary search tree, and we will be building a solution in JavaScript and also compute the time complexity and space complexity of the solution that we will be building. What does this binary search tree mean? It means that each node that you have, on the left side, the node will have a lower value, and on the right side, the node will have a higher value compared to the current node. And this will stay true throughout your BST. That's what is followed by a binary search tree. And in this tree, the problem statement says that you will be given a node that you want to find, and you go into this tree and then you try to find the node, whether it exists in the tree or not. If it exists, return that node. If it doesn't exist, just return null. What we are going to do is we will start with a specific node, let's say 5 in this case, and we want to search this 3 node which you have with value 3. We will say start with your root node, check if that itself is the node you want to find. If that is the node you want to find, just return it. Or if the node that you currently at is a null node, then you return null. If not, then what we will do is we will check the value that we want to find is less than your current node or it is greater than the current node. If it is less than the current node, then you will try to find the node in your left subtree. So in this case, this is a left subtree and this is a right subtree. So we will try to find in the left subtree if the key you want to find is less than your value of your current node. And then just go into recursion and say, hey, now this is my current node, which is going to be this one. And I will again say, hey, is this the node you want to find? Yes, that was the node I wanted to find, and then I just return this node. And similarly, if this 6 is the node that I wanted to find, what I would have done is instead of comparing 3 with 5, I would have said compare 6 with 5, and 6 is greater than 5. That would mean that I have to traverse the right subtree. So root.right is 6. I would have passed 6, and then I would have found 6 saying, hey, 6 is the node I want to find, and I just return this one. And that's pretty much the logic aspect of it. We just go recursively in the left subtree and the right subtree and keep trying to find the node that you are looking for. And this will translate into code into something like this. We will say that if root is null or root dot value is equal to the value that you are trying to find, then just return the root itself. This is going to be our exit condition from recursion. This will take care of leaf nodes. As soon as you reach the end of the depth of your BST, there won't be any leaf nodes on the left side or the right side. That is going to be the leaf node itself, which basically means it's not going to have anything on the left or anything on the right in terms of nodes. And this is going to be a matching criteria wherein I will say the value of my current root is what I'm looking for. Then I have basically found my root that I was looking for. Otherwise, what I will do is return. I will check if the value that I'm looking for is less than the value of my current node that I have. If it is less, then I will look into the left BST. So I will just say root.left, look in the left tree, or if it is greater, then just look in the right BST. And that's pretty much it. We just check here if the value matches, and then if it is not matching, we keep on trying to see if it matches, and ultimately you might either find it or reach the leaf node, in which case you will just return null because the root itself is null when you reach the leaf node and you have not yet found what you're looking for. So this is the whole mechanism using recursion. And in terms of time complexity, what I will say is it is going to be big O of h, stating that h is going to be the height of the BST, or it can also be, in worst case, big O of n, saying that you have a huge depth, and in that case it can even go to big O of n, where n is the depth of your BST, which is very high. In average case, you can also say it is big O of log of n in terms of time complexity, because then it gradually increases depending on the depth of your binary search tree. So this is big O of h, saying like the height, the depth of your binary search tree. And in terms of space complexity, that is also going to be big O of h, where h is the height of your binary search tree. And in worst case, it can be big O of n, because the space that is being occupied is recursive. So you are making this recursive calls. So the call stack is going to occupy space when you make these calls. And then once you return, it's just going to get popped. But the space it's going to acquire is equivalent to the number of calls you are making, which is going to be equivalent to the height of your binary search tree. And in worst case, it can be big O of n. It can be a very high number. And yeah, in average case, it could also be big O of log of n, wherein in that case it will gradually increase depending on the depth of your binary search tree. And that's pretty much it. Thank you for watching. Please like and subscribe.